Hello everyone, I welcome you all in this lecture. So in this lecture, we are going to study how to hold the altitude of an aircraft in an automated manner. Basically, we will study the altitude hold control. So theory we will discuss, block diagram we will draw, and finally we will implement in the MATLAB simulink. Altitude hold controller, you can say. Okay. Now, so already I explained to you about the aircraft pitch rate control. In this we have derived the pitch rate versus elevator deflection transfer function, and we have seen how to stabilize the pitch rate, and from that loop how to control the pitch angle. So in that loop we will add one more loop, that is called most outer loop, also called altitude hold loop. Okay, so if you currently remember, so we have drawn this slide q by Delhi transfer function, right? And we have imposed the physical limit as well. So in the physical limit, already I explained to you, first you have to put the rate limit, then position limit, and then actuator dynamics. Okay, that means how fast your actuator is going to deflect upward and downward. Let's say 40 degree per second, that limit you have to put, and then minus 10 degree to plus 10 degree, that you have to put as a position limit, and then finally actuator dynamics, that you can consider as a first order or second order. If you don't know, then it is better to consider the first order dynamics. Okay, now so finally q will come and you will integrate, you will get theta. Okay, and here what you can do, you can take a feedback of a q and multiply by the gain kq to stabilize first. Okay, so that basically this loop is most inner loop, also called the stabilization loop, because in a feedback you are multiplying. So already I explained to you what do you mean by the tracking controller and a stabilization controller. And in a stabilization controller, basically you are artificially improving the damping of a aircraft. Okay, all right. So after that, here you will have a PI controller, and here you will get the feedback of a theta, right? Up to this we are clear. Here you can command some theta value, theta command value. Okay, now from this we will add one more loop. Okay, so instead of directly commanding the theta, we will generate theta command by this. How will you get, now you are going to control altitude, right? So how will you get from theta to h, like from q to theta by integrating you got, right? So how will you get from theta to h? So that actually we can get, we know already, as I explained to you, aircraft dynamics, complete aircraft 6 degree of freedom. There I have told you about the rotation matrix, if you are correctly remembering. Okay, so the transformation from, for example, body to inertial, right? There is a transformation matrix, and here you have a UVW, velocity in body frame. So velocity in body frame multiplied by the rotation matrix, you will get the velocity in inertial frame. Here, let's say if you are controlling the altitude, so you are not moving laterally, and also you can approximate as a small angle of flight, which angle is a small angle of, and since the aircraft is not changing the altitude, so angle of attack is also in small, from theta equal to alpha plus gamma. Gamma is a flight path angle, right? Gamma is 0 in steady state level flight. Alpha is, theta is small, so alpha will be small, right? So in this case, you can consider as a V and W small, so only dominant term will be W. Okay. If you currently remember, we have written this as a plus sign theta in that matrix. If you are considering this H dot, okay. So H dot you can write U sine theta, or if you are not going to use this, you can use simple fundamental. From the fundamental you can get, actually this is, let's say, horizontal, this is a aircraft chord, wing chord, along this you are taking as a velocity, and this is a theta. So vertical component will be u sine theta and horizontal component is u cos theta, but I am interested in vertical component. So what vertical velocity you can write h dot, which is nothing but u sine theta. Same, right? Now why I am writing u, I can write v, right? Since u square plus v square plus w square, right? So if this part is small, then you can write v equal to u. So I can write here simply v sine theta, and if theta is small, you can write just v theta. Okay. And if you integrate h dot, you will get h. So basically here you will multiply by v, and then when you integrate, for example, or here you can integrate, you will get the h, right? And here you take a feedback and complete this loop. So here you can command some h value. For compensation, you will use PI controller here. Okay. So that is how you hold the altitude. So basically, when you use only one loop, can you can make call as a rate loop. Then here basically what you are doing, basically Q command is generated here, and here theta command is generated here. Okay. So basically when you take an entire control architecture, so Q command and theta command basically automatically generated. Okay. All right. Okay. So you are getting my point, right? Ki how I am moving from Q by delta E to Q, then controlling theta and then H. First stabilizing, then controlling theta, and then finally holding the altitude. Okay. So in this thing, how many things you are basically controlling? Three things, right? Basically Q, theta, and H. Finally H. So here there is a three loop. So most inner loop is what? This, right? What you call starting from Q command and ending with. So basically this is called most inner loop. You just call it inner loop, right? And after this, theta command is generated here. So basically this you can call as a, this also will be the inner loop, but you can call it a middle loop. Okay. And basically, what is the third one? This loop. This is called outer loop. Okay. So motional loop, middle loop, and then finally outer loop. Okay. So here you can see, let's say this is a 1, this is a 2, and this is a third. So first one is stabilization loop and remaining two loops are the tracking loop, because you are going to track the theta value, you are going to track the altitude value, right? And basically here you are stabilizing. One more thing I wanted to tell you here, these three loop is separated by the proper bandwidth. I mean to say, inner loop will be run at a higher frequency and outer loop will be run at a lower frequency, and the middle loop frequency will be in between the inner loop and outer loop. That means this fast loop, then little fast, and then slower. Okay. Why we are doing this? Because if inner loop is fast, then it will be good to reject the disturbance. Consider the quad rotor case, perfectly hovering, and some wind is coming from that direction, this direction, right? So what the wind will do, it will try to drag the quad rotor in this direction. So what is the clever way to do? Immediately you have to roll and counter that. If you are slow, then what will happen? It will drag, and then you will take a roll and bring back again. So unnecessary, this is a waste of time. Immediately you have to correct. That is why roll fast. Okay, that is why this is the, you have to generate faster roll rate, right? So that is why here the rate group should be act as a fast, whether it is roll rate or pitch rate. Okay. So that is a basic logic behind keeping the inner loop fast. Okay. So that means as a flight computer, when you take the data from gyroscope, accelerometer and all, so this as a most inner loop, rate loop will run at a higher frequency, and then the angle loop will be little slower, and then finally position will be the most slower loop. Okay. All right. So see, this is a pi I am using. So p means proportional, I means integral. So you can, I have already explained to you how to select the gain using Ziegler-Nicholas method, and you can keep you just select p and keep there is a one way to keep I, like from 5 to 27, 5 to 30%, to just select the p value, and from the p value you can actually find out the I value, which is approximately, or you can put just a 5 to 30%. Okay. This feedback gain is very much important, because this decides how much artificially you are providing the damping. It might possible that you will have a damping of 0.11 in a natural response case, that is not desirable at all. So by you multiplying this feedback gain, actually you can artificially increase the damping to from point, let's say 1 to 0.7. That's good enough. Okay. Although if you have any question related to this loop, and one more thing I will try to explain here. Here I am not including any kind of disturbance. See, there is a no disturbance in any of this summing junction, right? There is no disturbance in input and no disturbance in output. So as of now, we are not considering any kind of disturbance in the controller design, and also we are not considering any kind of delay and all. So, but in the future we will consider. Although we are considering this physical limit, but in the future we will try to include the delay as well as the disturbances. Okay. All right. because a delay, I mean to say, you are taking the feedback, so sensor will sense, it will take some time to send to the flight computer, there is a transport kind of delay, there will be computational delay, so there will be a lot of delays there. So basically you can actually consider the 40 millisecond delay or 80 millisecond delay. Okay, all right. Okay, so if you have any question regarding this loop, you can put the same in the comment section. Okay, I will be happy to answer. I hope you are getting all this point. Okay, so here delta is going, right? Delta I. All right. Okay, so we are going to implement the same in the MATLAB and Simulink in the next lecture. Thank you so much.